Good evening, ladies and gentlemen. My name is David Aguilar. I'm your host here at the Harvard-Smithsonian Center for Astrophysics in balmy Cambridge, Massachusetts. We're here tonight for a very special event. We've brought together some amazing speakers to talk about a topic that is dear to my heart and I think dear to many people who occupy the planet Earth. Now, of course, we know this is the 50th anniversary, and 50th anniversaries are something very special. And of course, this one certainly is, because we know it's the 50th anniversary of the Beatles coming to America. But with that said, and all the media coverage that we've had over the Beatles coming to America, it's been rather quiet. Because in a distant field in New Jersey, two young researchers with an aluminum ear were listening to entirely different music than anybody else had ever heard on planet Earth. They were listening to something that they didn't know what it was. And yet, when it was discovered what message was being sent to us here on Earth, it changed us forever. I want you for 1 minute to empty your minds, close your eyes, and imagine nothing. Nothing. Nothing exists. There is no universe. There are no stars, no planets, nothing. And then it all begins to exist. That's what we're going to talk about tonight. The beginning of the universe, the possible end of the universe, and everything in between. Assembled to guide us on this amazing journey through our lifetimes and this planet and this universe are four of the most unbelievable speakers that we could assemble at one spot, at one moment in time, to discuss their findings, their knowledge, and their understanding of the universe. Joining us here tonight will be Dr. Robert Kirshner, Dr. Alan Guth, Dr. Avi Loeb, and Dr. Robert Wilson. All have worked in the quest to try and understand this universe and our place in it. And who better to begin with than Dr. Alan Guth, MIT professor of physics and cosmology. His latest book, The Inflationary Universe, The Quest for a New Theory of Cosmic Origins, discusses 1/1 of 1/1 of 1/1 of a second after the Big Bang. Now, Dr. Guth, of course, was the 2012, the first winner of the Fundamental Physics Prize presented by Yuri Milner, an entrepreneur that started this new prize. But I think more importantly, and following in the footsteps of that prize, I think he should be very proud of his 2005 Boston Globe Prize for the messiest office on this planet. Dr. Alan Guth.
Now, which button do I push to get my slides?
Yeah, right. No, we need to get the presentation.
Oh. No. We'll get this working. Don't worry, folks. Okay, it's a real pleasure and honor to be invited to speak at tonight's celebration of what is possibly the most important astronomical discovery of the last century. And it's a special honor to be speaking immediately before Bob Wilson, who is one of the people who is directly involved in that discovery. So what we'll be talking about here is what we know about the origin of the universe itself. The classic paper that we are celebrating appeared in the Astrophysical Journal in 1965. You would think that this humongous astronomical discovery would be some humongous paper with loads of graphs and tables and whatever. But this is the whole paper right here. It sits on 3 pages, doesn't even fill the 3 pages. It starts at the bottom of the first page and ends in the middle of the second page. That's it. You probably can't quite read it here, but I've enlarged the title and abstract. The title is also surprisingly innocuous for a great astronomical discovery. If you were skimming over titles, you'd probably not even be attracted to this one. A measurement of excess antenna temperature at 4080 megacycles per second. A really bold title. The abstract is similarly bold. Measurements of the effective zenith noise temperature of the 20-foot horn reflector at Crawford, Hogg and Hunt, 1961, at the Crawford Hill Laboratory, Holmdel, New Jersey, at 4080 megacycles per second, have yielded a value about 3.5 K higher than expected. This excess temperature is, within the limits of our observations, isotropic, unpolarized, and free from seasonal variations over a specified period of time. A possible explanation for the observed excess noise temperature is the one given by Dickey, Peebles, Roll, and Wilkinson in a companion letter in this issue. Well, fortunately, this possible explanation is the one that we now all accept, which is what makes this such a fantastic discovery. This really was the clinching piece of evidence for the Big Bang Theory. Now, I suspect that many of the people in the audience here were born at a time when the so-called steady-state theory had already totally met its demise. So it may be hard to conceive of the idea that the Big Bang Theory was not always the theory that everybody thought was right. But in fact, in 1965, there were 2 competing theories. The Big Bang Theory, which was pretty much enunciated by Alexander Friedman in 1922 and developed further by Georges Lemaitre in 27 and Gamow, Alpher, and Herman in the 40s and 50s. But there was also the steady-state theory, first proposed by Sir James Jeans in 1928, and then elaborated very significantly by Hoyle, Gold, and Bondi in 1948. Now, I don't really know a lot, I confess, about the history and sociology of what was going on in the scientific community at this time. But if you just look at this list of names, notice that on the right there are 4 sirs, 3 sirs, I can't count that well. These were the scientific elite of British scientific establishment in Cambridge, Oxford, and so on. On the left, these names are now pretty famous because they were involved in the invention of the Big Bang Theory. But at the time, I doubt anybody thought that much of them. Alexander Friedman was really an obscure Russian meteorologist who wrote down these equations in 1922. He also, from the point of view of public relations, had the unfortunate situation that by the time he was my age, he had been dead for almost 30 years. I stole that from Tom Lehrer, by the way. But he died at the age of 37, and for scientists, longevity certainly always helps to publicize one's work. Georges Lemaitre was a Belgian Jesuit priest, hardly at the center of the scientific establishment. It was true that he had a PhD from MIT as well in physics, and did in fact significant work here at the CFA as well. But nonetheless, he was by no means the center of the scientific establishment. Gamow was a Russian immigrant, known for drinking a lot of vodka. Again, hardly the real image of all the sirs that are on the other side of the screen there. So certainly, it's a fact that many of the scientific leaders of the time were adherents of this steady-state theory, a theory which held that the universe, as it expanded, continually created new matter so that the density of the universe remained fixed and the universe could be absolutely eternal while expanding all the time. You might think, by the way, that you could rule out a theory like this by looking for matter production and discovering it's not there. But it turns out that it only takes an incredibly small amount of matter production to make this steady-state theory work. It only takes the production of about 2 hydrogen atoms per cubic meter per billion years. So it's awfully hard to detect. So even to this day, we have not ruled out the conceivable possibility that matter could somehow be appearing in the universe at that ridiculously small rate. So, in any case, this discovery of the cosmic background radiation really had no sensible explanation in the context of the steady state theory, although people tried, of course. And ultimately, it led, I think, the entire scientific community to be convinced that the Big Bang theory is the right theory. So here's the picture of the Big Bang as it was illustrated by the NASA WMAP team. The universe somehow began, presumably in some kind of a quantum process, which initiates the Big Bang. Then there's a very brief period of inflation. Not everybody is convinced that inflation happened, but I am, and they are, so it's pretty good. Then, at about 380,000 years after the Big Bang, was a very important event in terms of our cosmic background radiation, what we're talking about tonight. Until this time, the universe was so hot that it was a plasma. And plasmas are very opaque, very non-transparent to electromagnetic radiation. So the photons that filled the universe right from the beginning didn't go anywhere during this first 380,000 years. Each photon at any given instant would have been traveling at the speed of light, but it would constantly be ricocheting and changing directions, and the net effect would be that the light goes nowhere during that time period. But at 380,000 years after the Big Bang, according to our calculations, the universe finally cooled to the point that it was transparent to electromagnetic radiation. And that means that the light that we now see in the cosmic background radiation, the photons, have been traveling on straight lines since about 380,000 years after the Big Bang. And for that reason, they really give us a picture of what the universe looked like at that time, just as the light traveling from my face to your eyes gives you a picture of what I look like. So that's the magic time. The cosmic background radiation really is a picture of the universe at that time. Then very little happened for a while. Then stars started to form and galaxies. Then later, about 5 or 6 or maybe 7 billion years ago, the universe started accelerating again. And Bob Kirshner will be talking about that. He's one of the discoverers of that rather amazing fact. Okay, how does this Big Bang picture work? The picture is basically the idea that the universe as we know it began some 13, 14 billion years ago. And now we think we even know pretty accurately, 13.82 plus or minus 0.5 billion years, according to the latest estimate by the Planck satellite team. What existed before that, one might ask? Well, who knows? It's often said that time itself began at that instant, and that's certainly a possibility. But I think we really don't know, and there certainly are many other speculations in the scientific community by a number of people, including me, for example. Within about 10 to the minus 35 seconds of this beginning, inflation, we think, began. And what is inflation? Inflation is a theory about what I would like to call the bang of the Big Bang. Whoops. Yeah. What I like to call the bang of the Big Bang. And by that I mean the force that drove the universe into this humongous expansion that we call the Big Bang and that we're still actually experiencing. The universe is still expanding, largely as a result of that initial push that the universe somehow underwent in its first few instants. I might add that before the possibility of inflation was known, Big Bang theorists really had no explanation at all for the expansion. They just took the expansion as a given. The theory of the Big Bang prior to inflation was really only the theory of the aftermath of a bang. All the matter was already present and already expanding at the time that the scientific description of the Big Bang began. But inflation can explain the bang of the bang, the propulsion, by gravitational repulsion. According to inflation, it's a gravitational effect. Now, you may be surprised to hear that gravity can repel. We're accustomed to the idea that gravity attracts. And indeed, in Newtonian gravity, gravity is always purely attractive. Newton would have riled at the idea that gravity could somehow behave repulsively. But inflation depends on what I sometimes like to say is two miraculous features of physics, and one of those is gravitational repulsion, which has been part of physics as we know it since the advent of general relativity. Einstein himself used this option in the form of the cosmological constant to build a model of the universe that was static, with this repulsive force balancing the normal attractive force of gravity, preventing his model universe from collapsing. This did not turn out to be a good model for the universe, but it was an illustration of this repulsive gravity effect. And what's happened since is that modern particle physics suggests fairly clearly that at super high energies, by ordinary standards, there should exist materials that behave the same way, that produce this repulsive gravity. The other miracle which inflation is going to rely on is another peculiar feature of gravity, which is that it turns out that the energy of a gravitational field is not positive, but is actually negative. And this actually has been a feature even in Newtonian mechanics, although nobody made much of a deal of it until more recently. And you'll see in a minute how this plays an important role in inflation. So let me go over the sequence of events that we have in mind when we talk about inflation. Inflation proposes that at least a small patch of this repulsive gravity material, this very high energy material that can turn gravity on its head and make it repulsive, existed in the early universe. It didn't have to fill the early universe as long as there was a small patch of it. And we don't really know at what energy scale inflation really happened at, but a very plausible scale is the scale of what physicists call grand unified theories. And I'll give you numerical examples associated with that scale, although there's significant flexibility if inflation happened at a different scale. But at the grand unified scale, this initial patch could be as small as 10 to the minus 28 centimeters across. Unbelievably small. And since this patch is going to be enlarged fantastically by inflation, the initial density of these patches, or the probability that such a patch forms in any given place, can be incredibly low, because after a little while these patches will take over, even if they're initially incredibly rare. Once one has such a patch, the gravitational repulsion becomes the driving force behind a Big Bang within that patch. The Big Bang would become a local property in inflationary theory. The patch would be driven into exponential expansion, which means that it will double in size and then redouble in the same time and then redouble again in the same amount of time. And this doubling time would be as small as 10 to the minus 38 seconds if we're talking about the scale of these grand unified theories. So the patch would have to expand exponentially by at least a factor of 10 to the 28th power to make this work. But that's easy. It turns out it only takes about 100 doublings to expand to 10 to the 28th power. And it could have expanded much more. It doesn't have to stop then. There's no fine-tuning needed in the amount of expansion. There's just a minimum. And at the end, the region that's destined to become the presently observed universe was still very small, about the size of a marble. But then it keeps coasting bigger and bigger up to the present time, by which time it's large enough to encompass everything that we see. Inflation ends because this repulsive gravity material is fundamentally unstable, so it decays. And when I say it decays, I don't mean it rots. I mean it decays in the same sense that a radioactive material decays. It converts itself into ordinary matter, which is no longer gravitationally repulsive. And the gravitational repulsion turns off. And this ordinary matter rapidly forms a hot soup of ordinary particles, sometimes called a primordial soup. And this is the starting point for the conventional Big Bang theory. Inflation is now over, and it joins very smoothly onto the ideas that Big Bang theorists had before inflation was discussed. Now, a key and very important feature of this whole process is that during the exponential expansion, the density of matter and energy did not thin out. As the region expanded, the density of matter and energy inside the region remained essentially constant. Now, that seems very strange, because we all know that there's a principle of physics called the conservation of energy, which says that you can't make energy for nothing. So if we have a region that's filled with energy and expanding with energy of the same density, it means the total energy inside that region is going up and up. It doesn't seem to make any sense. But here is where that negative energy of gravity comes in as an important feature. Because the gravity contributes a negative energy to this whole system, the total energy can remain very, very small and constant, and could in fact, and I would guess very plausibly is, exactly equal to zero. And I have a little picture of what that means if it drives it home better. The total energy of the universe has a large positive contribution of matter and radiation, and that's drawn as black the way my accountant would draw it. And then there's a piece in the red, which is the energy of gravity, which is actually negative, and the total balances out to something very, very small and very possibly zero. So that's how inflation works. I'd like to spend the remaining few minutes here talking about some of the evidence that our universe actually underwent this process called inflation. And I want to point to three pieces of evidence, the first of which is the large-scale uniformity of the universe. The cosmic background radiation is uniform in temperature, we now know, to about 1 part in 100,000, incredibly uniform. Now, since it was released when the universe was about 400,000 years old, this implies that the universe was already incredibly uniform at this magic time of 400,000 or 380,000, I called it earlier, years after the Big Bang. Now, if the universe did not start out completely uniform, and we don't know of any reason why it should, although it might have, we don't really know, but if we don't want to just assume the uniformity, but want to ask, can we invent a physical process that would create the uniformity? In order to do it in this amount of time within conventional cosmology without inflation, you would have to be able to push the energy around at about 100 times the speed of light to be able to even things out on such a large scale so quickly. And that's not possible by any mechanism that we know. But inflation takes care of that in a very simple and, I would say, elegant way. Inflation just builds into our history of the universe a short period of humongous expansion, this accelerated expansion during the period of inflation. That means that if we follow the history of the universe back to before this spurt of expansion caused by inflation, the universe would have been much smaller than it would have been in a model without inflation. And it's at this very early time before inflation that the uniformity of our universe could be created, at a time when the universe was so small that there was plenty of time for the matter in the universe to smooth itself out, just as the air in this room smooths itself out. So the air pressure is the same on all parts of the room, and the temperature is also pretty much the same. So the smoothness occurs early before inflation on a tiny, tiny, tiny scale. Then inflation takes this tiny uniform region and stretches it to become large enough to include everything that we observe. Another important piece of evidence for inflation concerns the mass density of the universe. Astronomers and cosmologists measure the mass density in terms of a quantity called omega, which is the actual mass density divided by something called the critical density, where the critical density is that density which is necessary, according to general relativity, to make the universe geometrically flat. In any case, inflation predicts that this quantity called omega should be 1. The mass density should be equal to the critical density. Now, until about 1998, observations seemed to contradict that royally. Bob Kirshner here was always telling me that omega was 0.2 or 0.3. It was really irritating when I had dinner with him. He needled me the whole time. It was awful. But it turned out, in a sense, we were both right. The latest observation now of, again, coming from the Planck satellite, says that omega is 1.0010 plus or minus 0.0065. Pretty close to 1, just like inflation predicts, which is beautiful. The secret, the difference, is the discovery of a whole new form of matter, the dark energy, which indeed Bob was one of the key people involved in discovering it in the first place. And he will be talking more about that, I am confident. So now this all fits in beautifully with what inflation predicts. And finally, and this will be the last subject I'll talk about, inflation not only explains the large-scale uniformity of the universe by taking something very small and stretching it, but inflation can also explain the smaller-scale non-uniformities, which are so important to astronomy and to our existence. We are living on a lump of matter, the Earth, which is an example of one of these inhomogeneities. These inhomogeneities can be seen on a cosmic scale most clearly through the cosmic background radiation itself, where we now can measure these tiny non-uniformities at the level of 1 part in 100,000. And that, of course, leads to the question of, I can't even see what's on that. What does it say? 0. Oh, that's why I can't see it. I'll finish real soon. Just one more slide after this. Inflation has an answer to where these non-uniformities may have come from. According to inflation, it comes from quantum fluctuations, the inherent uncertainty of any quantum process. Classically, inflation would just stretch everything out and make it smooth. But when the classical prediction says everything is smooth, the quantum prediction is going to say that in some places the mass density will be a little bit higher than that, and other places will be a little bit lower than that. And that's exactly the kind of ripples that we see in the cosmic background radiation. And inflation, in fact, makes a prediction for what the spectrum of these ripples should look like. And by spectrum, I mean exactly the same thing as you would mean by the spectrum of sound waves. Any sound wave can be broken up into its different wavelengths, and you could talk about how much intensity there is at each wavelength. Astronomers do exactly the same thing to the pattern of energy in the cosmic microwave background. And here's the graph, and the data points are the data points. The green line is a fit to the inflationary models. There are some free parameters, I confess. But as you can see, there's just a beautiful agreement between the data and the form of the theoretical curve, making it look absolutely gorgeous for people who are enthusiasts of inflation. To be a little clear about what's being graphed here, the vertical axis is the intensity of these fluctuations as a function of the angular size on the top horizontal axis. On the bottom horizontal axis is something called the multiple moment, which if you know what it means, fine, but don't worry about it. It really just is another way of talking about the angular scale as shown on the top axis. So the bottom line is that the predictions of inflation seem to be working very well, and one of the most important ingredients in testing these predictions of inflation is indeed the cosmic background radiation, which has proven to be our best tracer of what we can learn about the early history of our universe. Thank you.
I can't think of anybody more excited about inflation than Alan, certainly not the Federal Reserve. But now we're going to take a step forward. I'd like to introduce Robert Wilson. He is a senior astronomer for the Smithsonian Astrophysical Observatory. In 1964, he and his colleague Arno Penzias, out in a large field, very successfully raising and housing pigeons, discovered the cosmic microwave background. His advisor, Fred Hoyle, had despairingly called it the Big Bang. And that's exactly what they had discovered. In 1978, Robert Wilson and Arno Penzias received the Nobel Prize for Physics for their discovery. Dr. Wilson.
How do we make it big? I guess down there. Okay, thank you. Well, in 1964, as you see there, Arno Penzias and I had been working about a year putting together a precision measuring system to work with the 20-foot horn reflector for several measurements that we wanted to make. And this measurement that I'm showing you here was the first one that we made in which we had the whole equipment together, and it immediately showed a problem. At that point, what we saw was that the antenna had almost twice as much noise as it was supposed to. It was hotter than the liquid helium rather than colder, and clearly this was a problem. It was a disappointment. In retrospect, this messy-looking record shows the most important thing that I ever measured. It's the first evidence we had for the cosmic background radiation. In this talk, I'd like to discuss how we got to this point, the source of the excess how the source of the excess noise was identified, and in the end, maybe a little retrospective about what it feels like to look back on it. I went to Caltech as a graduate student in 1957, and during my first semester there, Sputnik was launched. I knew this was an important event, but I didn't realize how important it was going to be for me. In the third quarter of the year, I had to join some research group to do a little bit instead of having a course, and I joined a new radio astronomy group. They had just completed the heavy construction for the Owens Valley Interferometer, and were about to build receivers and start making observations. So because of my interest in engineering and physics, this seemed like an ideal thing for me. Actually, as a graduate student, my one cosmology course was taught by Sir Fred Hoyle. And philosophically, I really liked the steady state theory with no beginning and no end. However, he wasn't my advisor, actually. In my thesis, I used one of the two antennas of this first Owens Valley Interferometer to make a map of the Milky Way. Since dish antennas tend to pick up some ground radiation as well as what they're looking at in the sky, and that varies depending on how you aim it. What I did was point to the west of the Milky Way and let the Earth's rotation scan my beam through it. And in those days, we didn't have computers, so there was a chart recorder, and you would see the power go up and down. And then later, I would take a meter stick, draw a line across the bottom, and measure above that. This was good enough for the Milky Way since it's very thin compared to its diameter, but it was clearly unsatisfying because here we are inside it, and nowhere we look would we have no Milky Way radiation. But there was nothing better I could do at that point. Meanwhile, at Bell Labs, John Pierce was a polymath who went around inspiring people to do things at Bell Labs. He wrote the book on electron guns to make electron beams. He contributed to communication theory. He started what I think was the first computer music project, and he wrote science fiction. I think probably the latter was the influence that made him think about putting a telephone repeater in orbit. Anyway, he wrote an article about this, and so when Sputnik went up and later NASA was planning to launch the Echo balloon, Bell Labs was ready to jump. He knew that the Echo balloon would not be a usable communication satellite, but it's always a good idea to start your experimentation with something fairly simple. So you use the very simple satellite and you learn how to track it. You'll probably learn a lot about what you have to know to do the more complicated thing. So they decided to put a big effort into that. Now we have a spherical balloon. When a wave comes up and hits it, it bounces off, it gets scattered in all directions. So the return signal is going to be very small. So they put together two Bell Labs inventions to make a very sensitive receiving system. A traveling wave Ruby maser, which had been actually built for the Cold War, and a large horn reflector antenna. The horn reflector would not pick up so much ground radiation that it overrode the maser's very low noise. So Echo was launched. It was used as a microwave relay. Eisenhower's voice was transmitted from JPL, received at Crawford Hill on the 20-foot horn reflector, and broadcast to the world over landlines. They had started Telstar. It was completed, launched in '62. The 20-foot horn was changed to receive one of the signals from Telstar. So after finishing my PhD, there had been a Caltech recruiter coming around our area, and I took a job at Bell Labs. Arno Penzias had been hired more than a year earlier. He had done a radio astronomy thesis with Charlie Towns at Columbia. He'd actually built a maser. So why did Bell Labs hire two radio astronomers? Are we going to make communications better? Well, I think the reason they told the management is that radio astronomers know about large antennas, They know about measuring weak signals or receiving weak signals through the Earth's atmosphere. It would be good to have a couple around to help us with satellite communications. But I think there are two other undercurrents here. One is that the group I joined was the same group, some of the same people who had been at Bell Labs in the 1930s when Carl Jansky discovered, if that's the right word, radio astronomy. Carl Jansky had discovered that there were signals coming from the galactic center, and that was the start of radio astronomy. Now that was the time of the Depression. They were working on short hours. It seemed important to do Bell system business rather than follow up leads like that. I think they felt bad afterward that that lead had not been pursued and wanted to do so. In fact, my first boss had roomed with Carl Jansky when they were first together at Bell Labs. The other thing is that Art Crawford, my first boss, who had built the 20-foot horn reflector, and the people who had made the maser were quite proud of what they'd done. And they wanted to see it be used for something more than just a passing satellite experiment. So they were happy to have a couple of astronomers around to actually make use of what they had done. The attraction to Arno and me was a very good research environment, generous support, and the opportunity to use the 20-foot horn reflector with a very low noise amplifier, which would make this relatively small antenna quite sensitive. Both Arno and I had used larger antennas, but there were special properties of the 20-foot horn reflector. This shows a picture of a few horn reflectors the way they were originally used on a microwave repeater tower. A weak signal would come in from somewhere, be received by one of them, and then a strong signal transmitted out to the next tower, maybe 20 miles away. This is the 20-foot horn reflector. It's been turned over on its side. And let's see if I can get the pointer to move around here. Can you see this? Yes. This is the reflector part, which is a piece of a paraboloid. So a wave coming in here is reflected down the horn and focused inside the cabin at the obvious place. You can see that there's shielding from the receiver all the way out to the reflector. And that does a very effective job of preventing ground radiation from getting into the receiver. The other wonderful thing about this antenna is that there's a large cabin out here which can support a lot of weight and doesn't move around with respect to gravity. So we could put very large receiving equipment in there. The maser itself must have weighed 1,000 pounds with its permanent magnet and all. And we put quite a bit of other stuff in there. So after I got there, Arno and I clearly were going to work together since there were two of us. And so we set down a little list of the things we thought we might want to do. The first was clear. We should measure the absolute strength of a radio source called Cas-A, which is the strongest in the sky, at 4 gigahertz. This would be useful for astronomy, and if we did it at 4 gigahertz, which was a satellite frequency, it could also be used to calibrate Earth station antennas. So it served the Bell system, and it was a service to astronomy. Then we would switch to about 1.4 gigahertz, which might include the hydrogen line, and we would look for a halo of radiation around the Milky Way and fix up Arno's thesis, which had been looking for hydrogen in clusters of galaxies. By starting with a 4 gigahertz system, we could make a null measurement for the halo of radiation of the Milky Way. We built the best measuring system we could. Arno made a liquid helium-cooled reference noise source. We're measuring thermal noise, so we usually refer to it by temperature. The higher the temperature, the more noise there is. It's just the most convenient way. I made an accurate switch and a radiometer system for comparing them. After assembling our radiometer, the first measurement, as I've said, was a big disappointment. The antenna was hotter than it should have been by about 3.5 degrees. This same effect had been seen earlier at Bell Labs, but had been dismissed because it was within experimental error. But we had a direct contradiction. By this time, though, Dave Hogg and I had measured the gain of the 20-foot horn reflector, and we didn't want to do anything to it until we had a chance to transfer that to celestial sources. So we spent 9 months improving our receiver, checking everything out, calibrating. And during that time, the 3.5K extra noise was always the same wherever we looked, unless we were looking at some specific source. During that time, we tried to think of everything we could to explain this extra noise, and we ruled out most of them. Since time's a little short, I'll talk about 2 of these things. There were a couple of pigeons living in the antenna. And we thought that pigeon droppings might actually make microwave radiation. They would absorb microwaves. So at some point we replaced the receiver with a pigeon trap, caught the pigeons, put them in a box, shipped them in the company mail as far away as we could, which was Whippany, New Jersey. We found the name of a pigeon fancier, sent them to him. He looked at them and said, "These are junk pigeons," and let them go. Well, what do you expect? 2 days later, pigeons are back. So, in the interest of science, our technician brought in a shotgun, and that was the end of the pigeons. Then Arno and I got up there in our lab coats with a broom and scrub brush and cleaned out the antenna. The other sort of unusual thing we thought about was that in 1962, there had been a high-altitude nuclear explosion out in the Pacific. I happened to be in Honolulu at the time, sort of celebrating my PhD, visiting my wife's sister, and the sky lit up like you wouldn't believe when this thing went off. It went off about sunset, but the sky just turned orange. David was talking about fantastic northern lights here. Well, you should have seen that. Northern lights on steroids. Anyway, it filled up the Van Allen belts, so we thought that was a possibility. But after a year, it hadn't changed, and those would have been decaying. Then one day, Arno called Bernie Burke, a fellow who now has been at MIT. And neither one of them remembers what the topic of the conversation was, but at the end, Bernie said, "What's going on with your crazy experiment?" Now, the background to that is that Arno and Bernie had been on an airplane going to Canada to some meeting, and Bernie had been saying, "What are you guys going to be doing at Bell Labs?" I think the implication, why aren't you at a real academic institution? Anyway, Arno had explained our plans, and Bernie had said, "There's no halo in the galaxy. You're wasting your time." So anyway, Arno laid it on him in this conversation. We had this extra 3.5 degrees. We can't find it anywhere. And he said, you should talk to Bob Dickey at Princeton. So what was the background of that? We knew Dickey had been interested in gravity theory. What we didn't know was that he'd been thinking about a Big Bang. He was thinking about an oscillating Big Bang and that it would be very hot. And as it expanded, the radiation in it would cool off. And he did a lot of microwave work during the Second World War for the radar effort. And he understood that it would become microwaves. So what does a university professor do when he has an idea? He got himself 2 postdocs. He was at Princeton. He got 2 very good postdocs. Jim Peebles was set to calculating what would happen in a Big Bang, and Dave Wilkinson started building a receiver to look for the resultant radiation. So Jim finished his calculation, someone at Johns Hopkins asked him to give a colloquium. He went to Dave and Bob Dickey and said, is it all right if I talk about my calculations? They say, yeah, we're so far ahead, no one could catch up with us. So he went off, gave the colloquium. A fellow named Ken Turner heard it. He was a good friend of Bernie Burke. He went back and told Bernie about it, and Arno happened to call the next day. So he told Arno about it. So Arno called Dickey, and it happened that the Gravity Group, as it was called, was having a sack lunch in Dickey's office. Phone rang. Dickey picked up the phone, started talking, and they heard atmospheric radiation, sky noise, antenna temperature, all the things they'd been thinking about. Their ears really pricked up. And after a few minutes, Dickey put the phone down and said, boys, we've been scooped. So we invited them over. They came over, and I think we were able to answer all of their questions about what might be right or wrong about our experiment. Arno and I were very happy to have any explanation at all at that point. However, we didn't take cosmology very seriously at that time. So we and Dickey's group wrote two separate papers. The short one you saw before about what we'd actually measured. We had previously published a much longer paper about the Cas-A measurement, which had all the details in it. And they wrote about the Big Bang and the noise that might be there. After one final check, we submitted our paper. But before the paper actually came out, Walter Sullivan was poking around the Astrophysical Journal office and got some hint of this. And he talked to us and the Princeton people and wrote a front page article in the New York Times on May 21st, 1965. That started me thinking that this cosmology business may have some real import. As a personal story, it happened that my father was visiting from Texas the night before. He had business in New Jersey, 3/4 of an hour away from where we were. I was still kind of a graduate student in thinking and got up sort of late, but he was a business guy and got up early. And he walked the 1/4 of a mile to the local drugstore, bought a New York Times, and came back. And there on the front page of the New York Times was our telescope and the article about the discovery. We were both very pleased, I think. So I'm here to tell you that these two guys in 1965 didn't know how big a thing they'd come across. It only came on later. I feel very lucky that I had the job at Bell Labs. Bell Labs supported us for taking Bell Labs technology and applying it to astrophysics. There were also many experts, people who had invented the things in microwaves that people use, who were there and were happy to answer questions. Another wonderful thing was I started my career when radio astronomy and cosmology were relatively young sciences, but poised to blossom as technology improved and people were able to measure more things. And at that time, partly thanks to Sputnik and partly thanks to what science had done during the Second World War, our nation was interested in supporting science and willing to spend the money to be the science and technological leader of the world. I was asked to convey the excitement of making the discovery. As you may have gathered from the talk, there was no aha moment in this discovery. There was a long period of trying to get to the bottom of our problem. The importance of the discovery really only became clear over time. It became clear as theory was developed and as receivers got better so that one could look farther into the background and see something more than just a completely featureless picture of this background. It's only the thing that Alan was talking about analyzing. However, it's been very satisfying to see all of this develop, to see the beautiful spectrum that Kobe produced. It's probably the world's best black body spectrum, and the wonderful WMAP and now Planck pictures that Alan showed the analysis of. So, it's been a wonderful journey. Thank you.
Thank you, Robert. Now we move up to our universe today. Our next speaker is Robert Kirshner. He's the Harvard Professor of Astronomy. His book, The Extravagant Universe, Exploding Stars, Dark Energy, and the Accelerating Cosmos, is a fun book to read, and I must say something about working with Bob Kirshner. He is one of the few astrophysicists I know that sees the humor in the universe and has such a marvelous way of translating it for all of us to understand and bring meaning to us, and yet at the same time impart knowledge that sometimes we don't even know we're gaining. In 2007, Robert shared the Gruber Prize for Cosmology. This is a huge prize for his work. He was involved, of course, in the expanding universe, and part of the Gruber Cosmology Prize, I heard you got a set of golf clubs and the deluxe home version of Wheel of Fortune. Dr. Robert Kirshner.
Thank you. Bobby, help me out here. Help me out here. Let's do a little time travel. 50 years into the future. No, into the present. Thank you. All right. Well, it's great to be here. Here's the idea. 13.7 billion years ago, the universe was hot and dense. We know it's hot because we see the radiation. Bob Wilson saw it, heard it with his radio telescope. And we also see that the universe is expanding, that the galaxies are moving out, moving apart from one another. And what I'm here to talk about tonight is very briefly to tell you that the expansion of the universe, which we've known about now since about 1930, is speeding up. And the thing that's making that happen is something very much like that mysterious anti-gravity stuff that Alan Guth was talking about. There's some property of space itself operating now much, much later in a much less energetic way, but nevertheless, some quality of space so that as the universe expands, the density of that stuff stays the same. It sounds familiar. And that could be the origin of the cosmic acceleration that we see. So that's the story I want to tell you. I better get going because it has a lot of moving parts. So I show you here a galaxy. This is a big system of about 100 billion stars, more or less like our own. But in this picture, if you look down in the lower left, you'll see that there's one star, which is, for a little while, glowing as brightly as many billions. And that's a supernova explosion in which the star has a thermonuclear explosion. It explodes like a bomb. Do not worry, the sun will not do this. And they are extremely bright, and we can use those to try to judge the distances to galaxies. The story really starts in 1917, more or less. At that point, Einstein was working away on his theory for general relativity, and astronomers were working on studying the universe. At that time, what astronomers meant by the universe was the Milky Way galaxy. They thought that that might be more or less it. But the most important thing in this picture is that little item over there, which is another galaxy. That's the Andromeda Galaxy M31, which is equivalent in size to the Milky Way, but just very much farther away. And as I'll show you, it's galaxies all the way out. So here's Einstein in a picture taken more or less in this period. This is a photograph taken on photographic emulsion, not like the electronic detectors that you have in cameras or phones today. And you can see that during the time the shutter was open, a guy left that seat. The other person back there disagrees with Einstein and is shaking his head. But the new thing that is really so impressive is that we're now scanning the plates the way we are scanning the Harvard plate collection so we can see what people were thinking. And Einstein was thinking that the universe must be static, that is, not expanding or contracting. And he said so, and he put a piece of mathematics into his equations to make that work. What he did was he put in a cosmological term, what we call the cosmological constant, and he said, this is in German, if you're in the back, I'm translating it. It says, that term is necessary only for the purpose of making possible a quasi-static distribution of matter as required by the fact of the small velocities of the stars. So people often say Einstein had a philosophical idea. Well, he may have had a philosophical idea about an eternal universe, but what he said was the reason is that he was talking about the actual measurements of stars in the Milky Way. And the velocities of the Milky Way stars are, in fact, small. But that was looking in the wrong place, because it isn't the properties of the Milky Way, it's the properties of those other galaxies, like the one I showed you a second ago with the yellow circle around it, are the ones that really matter. And the story of discovering that there was a big universe really began right in this building. Here's Henrietta Leavitt, who worked here at the Harvard College Observatory, and she worked on variable stars, stars that get bright and dim, and she noticed something very interesting about a particular kind of variable star. She said, it is worthy of notice that the brighter variables have the longer periods. The period is the time it takes to get bright and dim. It corresponds to the vibration, the physical change in size of the stars. So there's something that doesn't depend on the distance, that's the period of vibration, that can help you with the problem of finding distances, because if you're looking out into the night, you see stars, but some are bright, some are dim. You don't know which ones are nearby and which ones are far away. But if you can measure something, like the period, and find out how bright the star is, then you can properly assign it the distance that it ought to have. So people thought that was quite interesting. And one of the applications of that was to look at the Andromeda Galaxy. So here is a picture taken in 1923. It's a photographic plate. It's a negative. And what you can see here is the fuzzy ball. That's the same thing that I showed, like the galaxy I showed a minute ago. And then there's some markings on here. Up at the top, these things that are N. Hubble was looking for novae, so he marked them with N, where he thought they were new stars. But up at the top, there was something that was a nova, but then he said, gee, I see that one again. It was something was in fact a variable, and in fact, one of the same kinds of variables that Henrietta Leavitt had been studying at the Harvard College Observatory. He could measure its period and figure out how far away this thing was. This system is not part of the Milky Way. It's 2 million light years away. It takes light 2 million years to get here. And that was sort of the beginning of understanding that we live in a big universe. The other piece of it is, of course, we live in an expanding universe, a universe with motion. And here's Vesto Melvin Slifer at the Loeb Observatory with a spectrograph measuring the light from galaxies. Then from the light from galaxies, you can tell whether it's coming toward you or going away from you. What Slifer found is that with his little telescope and his little spectrograph, he could measure the velocities of a couple handsful of galaxies, and almost all of them are moving away from us. Well, Hubble put that information together, the velocity going up this way, distance going out that way, and what you can see is there's a good relation between those two. Well, actually, not so good a relation between those two. The data was pretty crummy at the beginning. It's always crummy at the beginning. It gets better over time. And here's what you see, and I'll show you some really crummy data. No, we had some crummy data too. But here's what you see. Over there is 0. And as you go farther away, this is the distance down here, the galaxies are moving away from us more rapidly. It's like something that's just stretching out in all directions. If by the power of the director of the Harvard-Smithsonian Center for Astrophysics, I could make this auditorium twice as big in the next second, what would you see? You'd see your neighbor, who's 1 seat away, would be 2 seats away. But somebody who's 4 seats away would end up 8, and somebody who's 8 would end up 16. The nearby people would seem to be moving away from you, if you can imagine this. The distant ones moving away from you more rapidly. But it's not because they know anything about you, okay? In fact, everybody would have the same view. So you'll notice that there's 0 here. This is the 0 line. And there are a few galaxies that are approaching us. It turns out that the Andromeda Galaxy, shown here, is approaching us. And this, have you checked your homeowner's insurance? Okay, so I know that most of the members of the Harvard faculty believe that this is the correct interpretation of the Hubble diagram. And I've discovered by teaching undergraduate classes that that view is shared by most of the undergraduates as well. That they believe that this shows what they've always known, that they are the center of things. However, as I just tried to indicate, it doesn't matter which of you takes the point of view of seeing the things moving away from you. If the space is stretching out in all directions, then everybody will see a universe that obeys Hubble's law. Okay, so the universe that we see is this complicated thing in which there are galaxies in the foreground and galaxies in the background. It's hard for us to sort out the distances. Some of them we can do, and if we can extend Hubble's law out to bigger distances. Bigger distances correspond to longer times. The light travels at the speed of light. That's a foot, which is a unit used in the United States and in Myanmar, in a nanosecond, a billionth of a second. So I see the people in the front row as they were a few billionths of a second ago, and the people in the back look younger because the light left them some time ago. Same thing you said, Alan. And so it must be true. So when we look out into the universe, we see 4 galaxies in the foreground, galaxies in the background, and it's our job to figure out what their distances are and to measure their velocities. If we do that, by looking at the distant ones, we can see what the universe was doing back then, when it was young. Well, Einstein gave up on that cosmological constant in the 1930s. And so if you go to the National Academy in Washington, there's a very nice statue of Einstein. Shows him historical details are correct, no socks. And it shows on this tablet, which he brought down from a mountain, a number of equations. There's the fundamental equation for general relativity, no lambda in it. Here's the photoelectric effect. They gave him the Nobel Prize for that, but he didn't bother to pick it up. And here's E equals mc squared. They were afraid to give him the Nobel Prize for that. Anyway, there's no lambda. Einstein more or less gave up on this cosmological constant because he had invented it to make a static universe. It's an anti-gravity sort of thing. If the universe was expanding, he said, well, never satisfactory anyway. Okay, so you can write down equations as Mr. Friedman did and Mr. Lemaitre did, and you can calculate what the history of the universe might be with different constituents in it. If it has gravitating stuff, that'll slow it down. If it has some of this cosmological constant, that could make things speed up. And so here's the idea. This is time down on this axis and size. Think of it as the separation between two galaxies over there. And when the universe is expanding, its size is getting bigger. It's going up on this diagram. If it's slowing down, that's a deceleration. It will be curved kind of downward. If it's accelerating, it'll be curved upward. So you already know the answer, so I'm not going to try to keep you in suspense. The answer, which was quite astonishing, is that we live in a universe which actually follows something like that red line, at least for now, and has, over the last 5 billion years or so, been accelerating. How do we know that? Georges Lemaitre is one of the guys who worked out the equations that show you how a cosmological constant would affect the expansion. And he's also one of the people who realized if there's expansion now, then the universe might have been smaller in the past. You could go back to some time, he thought, when there might have been kind of a primeval atom, which is really something we recognize as the Big Bang. And then he said in this kind of poetic way, the evolution of the world, and he means the whole universe, of the world can be compared to a display of fireworks that has just ended. Some few red wisps, ashes, and smoke. Standing on a well-chilled cinder, we see the slow fading of the suns, and we try to recall the vanished brilliance of the origins of worlds. Good. Good, George. This is just prose. Here we go. So how do we do this? How do we find out whether this expansion from this vanished past follows acceleration or not? You look deep into the universe. Here's the telescope in Chile that we used to do it. And now this photograph is taken without a flash or anything, with an electronic detector. And you know that you can do that now because the electronic detectors are 100 times more efficient than the photographic plates that Hubble was using. And we have something that's brighter than Henrietta Leavitt's stars to look at. We use supernovae, these exploding stars that burst out with about 4 billion times the light of the sun. They're about 1 million times brighter than the stars that Henrietta Leavitt was using. The problem is they're rare. You know, they're about 100 years apart. It's about 1 in a century. So even people like me or Owen, we have not seen a supernova in our own galaxy. It's been since 1604 since somebody has seen one in ours. So how do you get around that problem? You can't assign a graduate student the problem of staring at a galaxy for 100 years. They will not do it. And the answer is, of course, you have to look at a lot of galaxies. And the digital detectors that we have and the computers that we have allow us to do that. So here's an image. You can see lots of galaxies. Those are these little fuzzy things. But the galaxies that are really interesting are the ones that are very far, the ones that look just little like grains of sand in this picture. They look like little dots, but they are 100 billion stars at distances of billions of light years. Okay, and here's how you find the supernovae. You write software because it's too boring to look at these pictures. And you take a picture and compare it to a picture taken a month ago and subtract them in a computer. So things that stay the same, like this nice spiral galaxy, subtract away. And things that change are shown in the difference, and usually with a red circle around them. So that's a candidate for a supernova. You can take its spectrum the way Slipher did, and you can measure its brightness the way Hubble did, and you can put it on the Hubble diagram. And we've done that. So here is the Hubble diagram. Now this is a nice set of data, modern data, where, let's see, what is this? This is the velocity and that's the distance, but never mind. And you can see the data. And this curve that's going through it is for different cosmologies, different universes that have different amounts of this dark energy, the cosmological constant, or anyway, the springy stuff that makes the universe accelerate. And you can do this problem. Arturo, are you paying attention? You can do this problem. You watch this, and you see, ooh, that's good. Ooh, that's too much. It makes the Hubble diagram curve a little bit, and you can see it's as this ticks through about 0.7 that you get the best fit to the data. What that means is 3/4 of the universe is in the form of this weird dark energy, this strange stuff that we just discovered in 1998. So it looks easy now, but it was Galileo who said, all truths are easy to understand once they are discovered. The point is to discover them. So here's Einstein. Of course, he'd been dead for many decades, but in 1998, looking quite surprised, but he's carrying a sheaf of paper that has a lambda on it. He said, I thought of that. I could have been a good scientist, well known. Only I had stuck to my guns. Okay. And awards have been given for this. I, for example, received the XLR8N Universe license plate from the state of Maine. My students had to settle for a somewhat more Baroque prize awarded in some Scandinavian country. Saul Perlmutter, who was an undergraduate at Harvard, Brian Schmidt and Adam Rees, who were my graduate students, won the Nobel Prize in 2011 for the discovery of the accelerating expansion of the universe through observations of distant supernovae. Now they are shaking hands with some Swedish guy. And this information can be combined with other information. So here is a kind of picture, a baby picture of the universe, a picture of the glow from the Big Bang of the microwave background made into a picture. Most of the signal subtracted off, and what you're just seeing are the variations from place to place, the freckles sort of on the baby picture of the Big Bang. And just as I showed you that I got a somewhat inferior prize for my license plate and so on, I show you my own baby picture, which you can see over here won the Honorable Mention Award for the 16th Children's National Photograph Contest in 1950, just saying. Honorable mention. Again. Okay. So if you combine information from the microwave background, how galaxies are clustered, and other information, you can sort out how much of the universe is in each component. What you find is that atoms, the stuff that we're made of, it's about 4%. I don't know how that makes you feel. It makes me feel very special. There's other gravitating stuff that we call the cold dark matter. We're pretty sure that that is there and making the orbits in galaxies, but it's not the ordinary stuff that we're made of. And as you saw, as that line was ticking through the data points, about 3/4 of this diagram is labeled dark energy. Now, just because we can label it doesn't mean we know what it is. But it could be the cosmological constant or something very similar to it, and it could be very similar in its properties, is very similar in its properties, to the whatever that thing was that Alan Guth was talking about that makes the inflation take place in the first zillionth of a second. So it's something that is a mystery in science, and this is the best thing. If we have mysteries, if we have the unknown, we have something to do next year. Personally, I'm fond of the atoms, and my part of the pie is the tastiest part of the pie. At the Ig Nobel Prizes, I ate that, but anyway. So when you go onto the blogosphere, people say, oh, those scientists, they don't know what's really making this happen. The dark energy, dark matter, they're not too sure about it. But you know, we're used to judging the presence of things by the effects they produce. And what we see is this effect, the acceleration of the universe, the change in the expansion over time. If you look out the window on a windy day, you see the trees moving. And you know, if somebody asks you, well, what's happening? You say, well, it's the wind. You do not see the wind. You see the effects of the wind. And in the same way, we don't really see the dark energy, but we see the effects of it, and we can learn something about its properties by doing that. Finally, I'd just like to say this investigation is like a lot of things where we try to understand what the world is made of and how it works. And this is done by scientists in the way I've alluded to here, if not exactly shown. And it's also done by artists. You know, if you go to the Museum of Fine Arts, there's the masterpiece by Paul Gauguin. And, you know, he's asking the same kind of questions that we try to answer scientifically. Where do we come from? Where are we? Where are we going? Thank you.
Well, here we are. We're on the home stretch. Apparently, the universe began. It expanded. It's in a state today where it's expanding faster and faster, and it brings up the question, something audacious for a sentient species to ask, but what is the fate of our universe? Imagine all the creatures that have lived on this planet, all the creatures that never thought about this, never had the capability to answer that question, and yet here we are trying to answer it. And I can't think of anybody better to wrap this up tonight than Dr. Avi Loeb. He's a professor of science here at Harvard. He's the chair of the Harvard Science Department. He's the director of the Institute for Theory and Computation. He's the author of The First Light in the Universe, another book, The First Galaxies in the Universe, How Did the First Stars and Galaxies Form? And Time magazine awarded him the award of one of 25 most influential people in space. I didn't think it was that funny. But I'm never going to meet Albert Einstein. It's a time thing. I did meet Stephen Hawking once when he ran over my foot with his chair in the Caltech cafeteria. But Avi Loeb is better. Because Avi Loeb is one of those exceptional people that cruises the universe in his mind, and it makes sense to him. Dr. Avi Loeb.
So let me start with a confession. I've been working in cosmology for 20 years, and I'm fairly disappointed by now because all the objects that we heard about are dead objects. And as far as I'm concerned, the most interesting aspects of our existence have to do with life here on Earth. And so I would like to bring a human perspective into the discussion here. And I'll try to talk about things that are sort of down to earth, not too much out there. And here is a picture of the Earth that we are standing on. It's just a piece of rock. It was molten to start with. That's why it's roughly spherical once it's solidified. And the Earth is a piece of rock orbiting the Sun, which is one out of many stars, tens of billions of stars in the Milky Way galaxy, which is one out of hundreds of billions of galaxies in the universe. But surely there was a time when stars like the Sun and galaxies like the Milky Way galaxy did not exist, since the universe was much denser than these objects early on. And so trying to understand how we came to exist relates our existence to our cosmic roots. We would like to understand the story of Genesis in scientific terms. And that's what many cosmologists are doing right now. So that's why the study of cosmology is relevant. And the current picture, we currently have a standard model of cosmology. And in this picture, as Alan described, the universe is by and large uniform, but there are small inhomogeneities in it. And early on, these were small ripples in the density of matter that grew with time due to the unstable nature of gravity. So you can think of these as waves on the surface of a pond, but regions that were slightly denser than the average density of the universe became even denser with time because of the action of gravity. So more matter was driven into these regions, and eventually they collapsed to make bound objects like the Milky Way galaxy, inside of which the gas, the ordinary matter, was able to assemble, cool, and condense to the center and make fragment into stars like the Sun. So we can follow this picture and understand how we came to exist. And in fact, we can follow it quantitatively using numerical simulations. We can start with initial conditions that match the early conditions in the universe that we can observe by looking at the cosmic microwave background. And then feed those initial conditions into a computer simulation and try and figure out whether one ends up with galaxies that look like the Milky Way galaxy. And in fact, here you see a zoom in on a simulation that was actually generated here at the Harvard-Smithsonian Center for Astrophysics. And one of the galaxies here looks just like the Milky Way galaxy with a neighbor that looks like the Andromeda galaxy. So we are able to produce on the computer conditions that look just like the universe today from initial conditions that look like the cosmic microwave background at the early times. And that's very reassuring. It tells us that the laws of physics that we're using, based on what we see here on Earth, apply to the universe at large. This is not to be taken lightly because it's not at all obvious that we know all the fundamental principles that control the universe, but it turns out that we do a pretty good job starting from the initial conditions and ending up in systems that look just like the Milky Way galaxy. And here is a picture of our archaeological dig. So we're here in the center. Since the Big Bang took place 14 billion years ago, we can only see out to a certain distance because light propagated that distance since the Big Bang. So there is a spherical region around us that we can actually observe. We can't see anything beyond it because light from more distant regions did not have time to reach us by now. And so this is our archaeological dig. And as we go deeper into space within that volume, we're seeing how the universe looked like at earlier times. So the farther we dig into the universe, the earlier is the layer that we are uncovering. Just like an archaeological dig, except it's spherical around us. So any direction you dig, you are supposed to see the same thing, statistically speaking. And of course, if you want to go all the way back to the Big Bang, you need to go to the distance that light traveled over 14 billion years. But you can, so far, for example, we have an image of the universe from when the universe became transparent. And that's the cosmic microwave background that comes to us from a spherical shell around us that emitted that radiation. We can also map what is happening in between us and that distant photosphere that we observe in the cosmic microwave background. And what you see here is this redshift symbol that tells you how much the universe expanded since a given cosmic time. So if you see, for example, a redshift of 1,000, that's when the universe was relatively dense, and then it expanded by a factor of 1,000 since then. And that's where the microwave background is coming to us from. Now we can take images of the universe at very early times by going very deep into space, and this is one of these deepest images. And we can see galaxies in it that existed when the universe was 500 million years old, much younger than the present age of the universe by about a factor of 20 or so. And the way to identify those distant galaxies is to look at the absorption of light by hydrogen, which actually eats up part of the emission from those galaxies. And the longer the wavelength at which this absorption takes place, the higher is the redshift from where we see the light, because the wavelength of light is being stretched by a factor that is related to how much the universe expanded since the time that this radiation was emitted. And on the computers, we can in principle feed the initial conditions of the universe and figure out the answer to the question, when did the first stars form? And the current standard model of cosmology predicts that the first stars formed about several tens of millions of years after the Big Bang. And here you can see the results of such simulations. When you follow the formation of the very first clumps of ordinary matter that end up in stars, you find that those stars were actually more massive than the sun by a factor of 10 to 100. These were relatively massive stars because matter was hot early on, and the rate by which matter assembled onto the seeds that made the stars was higher than it is today. So these were very massive stars that started the process. And we can actually, in principle, measure or observe the effects of these stars, the environmental impact that these stars had because they emitted ultraviolet radiation, and that radiation broke the hydrogen that filled up the universe into its constituent electrons and protons. And you can see this process by observing the hydrogen. Hydrogen glows in a radiation that we can observe in the radio. And what we expect to see are holes in the distribution of hydrogen due to the first galaxies that emitted the radiation that broke the hydrogen in the vicinity of those galaxies. And this kind of a map is so far only available in plots that theorists made. But this technique of trying to image hydrogen is being pursued now by several groups around the globe in trying to really see the effects of the very first stars on the rest of the universe. Most of the discussion in cosmology is focused on dead objects, stars, galaxies, without any notion of life in them. And a very interesting question is, when did life begin in the universe? And so I was wondering about this question actually just a few months ago on Thanksgiving Day. And I realized that the first stars were actually made tens of millions of years after the Big Bang. That happens to be the time when the cosmic microwave background that Bob Wilson discovered had a temperature which is just room temperature on a sunny day. So that raises the possibility that if the first stars formed around that time and planets were made in the vicinity of those stars, then these planets do not really need the heat from their parent star. They can be heated by the cosmic microwave background. And one can have liquid water on the surface of these planets. So in principle, life could have started at that time. And the cosmic microwave background would act as an incubator that allows liquid water to exist on the surface of these planets and the chemistry of life to begin at that time. That was very early in the evolution of the universe. Now, even if the conditions were not right for making planets and allowing life to exist at that early time, this is absolutely the earliest time where life was possible. And more likely, life started somewhat later. And of course, 14 billion years later, we exist. But we might be just relatively latecomers to the game. And the universe might be full of life. It's very difficult, actually, to detect evidence for life elsewhere. Last summer, I tried to estimate how far away can we see, for example, a nuclear war that a civilization on an extrasolar planet has. And it turns out that even with the best telescopes at our disposal right now, we can't really see such an event at the distances of the nearest stars. So life actually produces very minute signals that are difficult to detect with present-day instrumentation. Now, so far I discussed the past, and since my two daughters are in the audience, they care mostly about the future, and I would like to now move from the past to our future and ask, what does the future hold for our universe? That's an interesting question. Most of my colleagues do not really worry about it because they say, well, it will take a while before the universe will change. We can't do observations of the future. Therefore, let's not think about it. They're very practical people. But to me, the intellectual value of a question doesn't depend on whether we already have the data for it or not. So I actually am very curious to figure out what happens in the future. And shortly after the discovery of the accelerated expansion of the universe, it occurred to me that, in fact, if we sit right here, and this is either us or the US, looking outward, we would see distant galaxies moving away from us. But their speed is increasing with time. And so if you wait long enough, eventually a distant galaxy will reach the speed of light. And what that means is that even light cannot bridge the gap that is being opened between that galaxy and us. So there is no way for extraterrestrials on that galaxy to communicate with us, to send any signal that will reach us once their galaxy is moving faster than light relative to us. And so that's an outcome of the accelerated expansion of the universe. All the galaxies that we currently see will eventually run away from us at a speed greater than the speed of light, and we won't be able to see their whereabouts after that time. And the more distant the galaxy is from us right now, the earlier this will happen. And in fact, all the galaxies above a redshift of 1.8 are already outside of our horizon. So if there is a cell phone out there trying to send us a signal, it wouldn't reach us anytime in the future. And the way to think of it is just like ants walking on the surface of a balloon. Imagine a person blowing up a balloon. The ants are moving on the surface at some speed. And you can think of these ants as analogs of photons, as radiation, particles of light moving in space. The photons have a finite speed, the speed of light, but space itself, which is represented here by the balloon, can in principle expand faster than photons propagate. And that's what happens in the accelerating universe. So these ants would visit only a small part of the surface of the balloon. They will not be able to communicate across large portions of the balloon if the balloon expands fast enough. And that's what happens in the accelerated expansion of space. The photons are unable to cover a region that is bigger than some scale. And in fact, if we look at the galaxies around us, out to a certain distance of, let's say, 300 million light years around us here in the upper left panel, there are a lot of galaxies within that distance right now. But once we wait a time that is roughly comparable to the present age of the universe, there would be fewer galaxies within that circle. And if we wait for 3 times the present age of the universe, even fewer galaxies. And eventually, if we wait 7 times the present age of the universe, we would only be able to see galaxies within this red circle here. So if we wait longer than 7 times the present age of the universe, eventually, we will not have many galaxies left within our observable volume of the universe. And you might ask, how many galaxies do we expect to find within our horizon once the universe ages by a factor of 10, once it's 100 billion years old? And the answer is only one galaxy, our own galaxy. So, and this galaxy, by the way, will not be just the Milky Way. We see the Andromeda galaxy, as Bob Kirshner pointed out, approaching us, and it will actually reach us earlier. And so we, together with a postdoctoral fellow here, T.J. Cox, back in 2007, we did a numerical simulation of the collision between the Milky Way and Andromeda, trying to figure out what will happen as a result. And this is the only paper of mine that has a chance of being cited in 5 billion years. And here you can see the collision in terms of the gas and the stars that make up these galaxies. Eventually, the 2 galaxies will merge to form a big ball of stars and gas. These are called elliptical galaxies. We see a lot of them. And presumably, they resulted from the mergers of disk galaxies like the Milky Way and Andromeda. It's interesting to wonder what will happen to the sun. And here are a bunch of stars on a ring at the same distance as the sun is from the center of the Milky Way galaxy. And throughout the collision, these stars are being scattered. Within just a couple of billion years, the Andromeda galaxy will come very close to the Milky Way. That's the first passage. And in fact, right now, Andromeda is very small, as you saw on the photographic plate that Bob Kirshner was showing us from Hubble's data. But if you wait 2 billion years, the Andromeda galaxy will just looming over our horizon will be as big as almost the entire sky, as big as the Milky Way. But the 2 galaxies will not merge at that time. And in fact, it's possible that the sun will be carried away with the Andromeda galaxy. So then we will see the Milky Way at a distance. That will be a beautiful sight. Eventually, the 2 galaxies will come together in a time that is shorter than the lifetime of the sun. So in fact, the sun would still shine at that time. And most of the stars that are currently at the same distance as the sun is from the center of the Milky Way will be scattered as a result of the merger to distances that are larger than present distance of the sun from the center of the Milky Way by a factor of a few. So let me summarize the state of the universe. We cosmologists are exploring the scientific version of the story of Genesis, let there be light, and future observations that are using the biggest telescopes we can construct, and also the radio observatories that will go after the faint glow of the hydrogen in the universe. they will be able to unravel the details of how the first stars formed in the early universe. So you might summarize it in one sentence. Religious ideas, ideas that were previously in the realm of religious texts, are now being explored by science. And that's a very encouraging development. But if we think about the future, the situation is quite disturbing, because the merger product between the Milky Way and Andromeda, which I decided to call Milkomeda, will be the only galaxy in the distant future that will be observable to us. In the entire universe, we will be surrounded by vacuum in the standard cosmological model. And so eventually we will lose sight of the evidence we had for the Big Bang. And in that sense, we will have textbooks or books that tell us a story about how the universe started that we will be unable to validate, to check whether they are true or not. We won't be able to do the experiment that Bob Wilson was describing in the distant future. So the question is, will cosmology become a religion at that point? There will be a story being told without us being able to verify whether it's correct or not. We will have to believe in it. So there is some regression in the distant future that we should expect. And in fact, it's even worse than that, because once the universe will age by a factor of 100, the wavelength of the cosmic microwave background that is currently 2 millimeters, so it's that big, and that's how Bob Wilson was able to detect it with the Horn antenna, it will be stretched to be 10 to the 28 centimeters, as big as the horizon of our observable universe. And so there will be no sense of an electromagnetic radiation to assign to this entity. The cosmic microwave background will not be measurable, even in principle, irrespective of how advanced the technology would be. You won't be able to detect an electromagnetic wave associated with the cosmic microwave background because its wavelength would be as big as the universe. And there will be no trace of the Big Bang, except that we actually had a snowstorm a couple of years ago where Harvard was shut down, and I was worried about this future, and it really bothered me that we won't have any evidence to the fact that the universe is expanding. We'll have only our own galaxy surrounded by vacuum. Is that really the case? And then I realized that, well, it's not exactly true, because our galaxy is spitting out stars continuously. And these stars are coming from the center of the Milky Way galaxy due to the interaction with the black hole at the center of the Milky Way. These are called hypervelocity stars, and are being ejected once per 100,000 years from the center of the Milky Way galaxy. And what would happen to these stars is that once they escape from our galaxy, they will be carried away by the cosmic expansion. So these stars could serve just like the galaxies that Edwin Hubble was looking at. You can see how they recede away from the Milky Way galaxy, and you can see their accelerated expansion. So you can use them as tracers of the cosmic expansion, and then you can try and figure out what really happened when Milkomeda was made, a long time before that time. And one can, in principle, figure out the conditions in the universe at those early times just from the properties of the Milkomeda galaxy and the fact that those stars are running away, telling us what the mean density of the vacuum is. So that is actually a very interesting thought, in the sense that 1 trillion years from now, it will still be possible to validate cosmology textbooks by watching these stars running away from the Milky Way galaxy. And of course, close to the center of the Milky Way, it's the gravity of the Milky Way that matters, but once these stars escape, the cosmic acceleration takes over and allows us to figure out that there was actually a Big Bang to start with. Thank you.
Thank you, Robbie. And that's it. In 80 minutes, we've taken you from the beginning of the universe to the state of where the universe is today to the possible end of the universe. And with that note, we're going to take a 5-minute break here from the Center for Astrophysics in Cambridge, Massachusetts, and we'll be returning with questions and answers in just 5 minutes. Q&A? Thank you. I'd like to ask all of you to come back to your seats. We do have some media people that are with us, and I would like to indulge them first. So some of our media folks right up in front here. If you have a question, I will repeat it once again for our other audience in the other rooms. Questions? All right, we're going to start in the back.
When you showed the example of bubble expanding of the ants on the surface, is space itself expanding? By that I mean, is the space between the atoms and the ants?
The question is space between the atoms expanding as the universe expands?
So are the ants getting bigger?
The ants are not getting bigger, but the separation between them gets bigger. And the reason the ants are not getting bigger, or if you want to think about it, for example, atoms are not getting bigger. Is this working? No?
Not very well.
It's on.
You have to speak close to it.
Okay. So systems that are held by forces, for example, stronger than gravity, are not being torn apart. And the gravitational effect of the vacuum, for example, that is allowing the universe to accelerate its expansion is fairly weak. So, for example, the Milky Way is not influenced by it. Atoms obviously are not influenced by it. And ants would not be influenced by it. However, the separation between objects will increase with time because space itself is not a rigid entity like Newton thought. It's actually a dynamical entity in Einstein's theory of gravity. And so length scales can change as a result of gravity, and that's what happens in the universe. Space itself is expanding. The objects are not really moving relative to their environment, but they are being separated from other objects just because space is expanding, and the expansion could be faster than light in principle, because you're talking about regions of space that are far away from each other. They can be separated at an arbitrary speed in general relativity.
And this has nothing to do with antimatter.
Another question? Yes, right up front. Yes, you.
I have a question about, it's a little bit away from Big Bang. Thanks for the nice talks. The question is there any alternative theory rather than Big Bang?
Is there any other alternative theory for the Big Bang?
Come on. Come on. Make one up.
Well, I think I'd sort of say there are things about the Big Bang we don't know. So there's plenty of room for more detailed theories. But at the moment, I would say that the Big Bang theory really is the only game in town. I haven't heard anybody talk seriously about alternatives. Maybe the other people here have, but I'll leave it at that.
I don't hang out with those people.
We had a question up front here.
Yeah. Hi, Miriam Kramer with Space.com. I'm just curious for Avi, what Hi, Bob. We've met.
Yes, hello, yes.
I'm wondering, what kind of life could have potentially formed in that primordial soup at the room temperature early universe?
Well, presumably primitive life, if at all. And I should have clarified that it's not really the very first stars, because you need to produce heavy elements in order to allow the chemistry of life. So you need water that has oxygen, and that's produced.
You need water?
Not really.
Maybe I wasn't listening here.
So you really need some exploding stars to start the process of dispersing heavy elements into their environment, and then planets could form, and then water in principle can exist on the surface of rocky planets like the Earth. And my expectation is that this would be primitive life. Now, the reason it's significant in a cosmological context is because people have been arguing that, in fact, the universe has the parameters that it has. For example, it has the vacuum energy density, or the cosmological constant, has just the value that is the maximum you can think of that would allow a galaxy like the Milky Way to exist within it. That's called the anthropic argument, saying that if the cosmological constant was much bigger, then the Milky Way would not be able to form, because the universe would accelerate earlier on before the Milky Way was made. And if you could make life much before the Milky Way was made, let's say tens of millions of years after the Big Bang, that would argue that the universe was not really designed for us to exist in it. The value of the cosmological constant could have been 1,000,000 times bigger, and you could still start life. It would take a while before you would develop complex forms of life, like intelligent observers, but they could eventually come out of it, and you don't need to have them immediately at the start. You can wait a few billion years, and then they will come out and observe the vacuum mass density that is 1,000,000 times bigger than the present one. So that's an argument against the anthropic argument, which some physicists have a problem with, because they believe that there should be a physical explanation to the value of the vacuum mass density, just like there should be some explanation to the mass of the electron. All kinds of fundamental constants that we measure might have some explanation. We don't know it right now, but we should not therefore assume that these values of fundamental constants were designed for us to, would not allow us to exist, therefore they must be the way they are.
Question here?
This is for, I'm Lisa Grossman from New Scientist. This is for Bob Wilson. You said something in your talk kind of offhanded about, at the time, science funding was great and everyone wanted to support science because of Sputnik and because of World War II. Could you comment on the state of things now? How it's changed in the half century since that?
I think I see less tendency of the nation to want to support fundamental science. The institutions like Bell Labs, probably IBM research, the industrially supported science is not going on now. The only way to keep this up is the government, and there seems to be a tendency to cut budgets rather than expand them. I don't know, how do you feel?
It's quite remarkable what Bell Labs did, because here is an organization that is supposed to aim at making a profit, and nevertheless assembled some of the best scientists in the world, not just in the context of radio astronomy, but also solid-state physics. And they did it from the point of view that in fact, if you bring a bunch of excellent people, put them in a corridor so that they speak to each other, and especially speak to experimentalists, they will come up with ideas that eventually will translate to devices that are useful, and that you can sell and make money, a profit out of. And that calculation is not being done these days, unfortunately.
Well, you know, it was a monopoly. And you know, there was just one phone company, and they owned your telephone. And you rented it from them for a few dollars a month. So, you know, the economic underpinnings of that great institution are something that we've changed.
Yes, when Bell Labs was started, no one else was doing the kind of research needed to make a better communication system.
Right.
By the end, there were lots of other companies willing to sell communications equipment. So things had really changed over that period. So in the beginning, Bell Labs got together scientists who when they found something new, would follow through. And what can this do for communications?
Good question. Question right here.
I saw on your slide the mention of the allusion to the big rip. So I was wondering, is there a limit to how much the to the acceleration? That is, as I understand it, with dark energy, new energy is not being created; it's just being transferred, you know, in making the universe larger. But if new energy is not being created, is there a limit to how fast it can tear itself apart?
Is there a limit to how fast the universe can be torn apart?
If the dark energy is really the cosmological constant, and it's really constant, then that was that red line that I had there.
Okay.
Braintree, alewife, moving upwards. It's literally exponential, which means that the rate of expansion depends on how big it is. You know, it's like just like compound interest. You know, they give you more money the more money you have. Why am I on this economic tear? Anyway, you know, the bigger it is, the faster it goes. But there's no guarantee that the relation between pressure and density is exactly the one of the cosmological constant. It could be something else. So it seems to me, from the point of view of an observer, that's the next thing to do, to measure as well as we can whether the expansion is really exponential and, you know, follows exactly what you predict for a dark energy that is the cosmological constant, or whether we see something else, which would be even more interesting. So there are possibilities that the energy changes faster than exponential, and those are the ones that in which the expansion of the universe will speed up even faster than that, and in which these kinds of diagrams that Avi was showing, where the galaxy would keep its own identity and the space would expand, are not valid. If the dark energy goes faster than that, the galaxies will get ripped apart, the atoms will get ripped apart. The Big Rip. It's a good name, and it's plenty scary. But whether it's real or not, we don't know.
Question?
Yeah, I have a question for Dr. Guth. So in your talk, you mentioned that one evidence for inflation is the small scale and uniformity, right? So,
right.
So the thing struck me is that if I thought the small scale and uniformity is due to quantum fluctuation, and I always thought that it comes from the Big Bang. So my question is, what's the order in time of inflation and the Big Bang?
Okay, the question pertained to the origin of these density fluctuations, and specifically the question of what is the order in time of inflation versus the Big Bang.
Yeah.
And that's a hard question to answer because the word Big Bang is a bit vague. People use it in all different ways. Some people use the word Big Bang to mean the ultimate origin of the universe, whenever that was, and that would have to come before inflation. But I usually think of inflation as the precursor of the Big Bang, defining the word Big Bang as the period of enormous expansion that we study, that we understand how the universe cools during the Big Bang and how the matter gradually congeals, and all that came after inflation.
So you think Big Bang is somewhat vague. How about inflation? Would you say there's just one inflation, or could there be more than one kind of inflation?
Well, no, certainly there could be more than one kind. I mean, there could have been many episodes of inflation, as far as we know.
There you go.
And it's also true that inflation is not really a specific theory. Inflation is really a whole class of theories, and we're still working hard to gain evidence to try to pin down the class of theories.
Is it falsifiable? Is it falsifiable?
Is inflation falsifiable? I think that's kind of a silly question.
Now we're going somewhere.
Inflation is really an ingredient of theories, and someday we'll pin down the right theory, and then I think we can decide whether we want to call it inflationary or not. But right now, I think there's very significant evidence that inflation is playing an important part in all the theories that we know of that are viable.
Is it possible to do an experiment that will falsify it?
Well, I think inflation is a little bit too flexible an idea for that to make sense. It's a little bit, I think, like in the particle theory context, for people who are familiar with particle theory, asking is there an experiment that could falsify gauge theories? And I think there are a lot of gauge theories, there are a lot of inflationary theories, and I don't think there's any one experiment that could falsify either concept. The real question is, when we finally settle on the right theory, will it be one that embodies those concepts? And I would say the evidence is very good for both gauge theories and inflation.
I'd like to thank you for opening up a can of worms. Right over here.
Professor Ali, so you said that the galaxies that we have, that we see at present, are accelerating away from us, and they can go out of sight at some point. Do you think there's already some information that has already gone out of our visible horizon? And if so, like what kind of implications would that make on our present-day theories?
Has there been information that's already receded and gone out of our horizon that we will not have access to is the question.
Yes, so first I should explain what happens to a galaxy once it recedes from us faster than light. Basically, the situation is similar to seeing a friend or a source of light falling into a black hole. There is a horizon, and you never see that person or, let's say, flashlight crossing the horizon. You see it approaching the horizon, fading away, and getting redder and redder. And sort of its image freezes at the point where it crosses the horizon, meaning that you can't really get information of what happened to that person after he or she went through the horizon. So the information is lost in the sense that you get just a frozen image of the point in time when that person crossed the horizon of the black hole. That's it. And the same happens in the case of the universe. A galaxy that is speeding away from us eventually crosses our horizon, but what we would see is a frozen image of that galaxy at the time when it reached the speed of light. Now, obviously there is lost information because we don't know the whereabouts, so we don't know what happened. We can't see exploding stars in that galaxy after that time. As I said during my presentation, galaxies that are beyond a redshift of 1.8 are at this point in time getting out of our horizon. So already for those galaxies, we are seeing light from those galaxies that left them a long time ago, billions of years ago. We see it arriving to us now, but the light that is leaving them right now will never reach us.
So if I understood you correctly, some of your friends are flashlights? Sorry, did you want to? All right.
I'd like to disagree slightly with Avi. Well, certainly what he says is in principle true, but as far as the numbers, I I disagree. It's true that objects which are currently at a redshift of 1.8 do have a velocity relative to us which is equal to the speed of light. That's a fact. That does not mean that the light from there will never reach us. If you calculate what happens, light from beyond there will initially move further away from us as time goes on because the light will come at the speed of light, but the whole space is moving away faster. But if you wait long enough, that light will still eventually reach us. It's only redshift infinity is still always the horizon, right, as far as what will not reach us.
We fade.
Well, the image is starting to fade, but there's nothing particular that happens at 1.8 as far as the image is concerned. It's part of the fading process, but I don't think it is in any sense the limit beyond what you will not see.
Well, send some of your friends out there with flashlights and look into it.
We'll take 3 more questions, beginning with the gentleman in orange, and then I will go upstairs.
I recently saw a TED Talk by, I believe it was Eric Weissner Gross, and he was talking about his theory of a new equation for intelligence, and saying that intelligence is a force and that it creates future possibilities. I'm wondering if any of the 4 of you have heard about that, especially Dr. Loeb, because it kind of hits on a number of points that you might have brought. Is there intelligence, early intelligence, or are we seeing the effects of it?
Yeah, this seems like a good question for us.
Well, from the point of view of physicists, there is nothing other than the particles of the standard model of physics and the forces that we know about. And so intelligence is just an assembly of elementary particles in some configuration that to us looks sophisticated. So in a way, that's not a new force. It's just organization of matter in some form that appeals to us. And the universe as a whole doesn't really care much about it. The question is, can we detect signals from other civilizations that are as intelligent as us or even more intelligent? Because if we do, then we can ask them, why is there a cosmological constant? What was inflation? If they had 1 billion years to figure it out, they know the answer by now. And unfortunately, I mean, that feels like cheating in an exam because you're asking someone else to give you the answer, but I think many of us would be quite happy to
Save some time.
Question from up above. Yeah, maybe Dr. Kirshner. If we're thinking about Andromeda and the Milky Way converging, is there any predictive or analytical use if one took, say, an inventory of elliptical galaxies to spiral galaxies and then say, well, all these ellipticals are a product of prior convergence? Does that give any kind of baseline to look into the nature of the expansion? Is it perhaps truncating and so on?
Yeah, no, it's an excellent question. So the question is whether galaxy mergers over time give you some clue to what the history of the universe has been. And the answer is yes, indeed. And we can take a look at the galaxies we see today. We can look at the galaxies that we see at redshift 1, so when the universe was about half its current age. And what we see is there was a lot more star formation going on then, presumably mostly because of these galaxy collisions. And then if you go twice as far back as that, it tailed off. There's less information, but there's less star formation probably. There's more of it shrouded in dust. It's a lot harder for us to know what's going on. But what we'd like to have is just the kind of story you're thinking about, in which the actors are the galaxies, where they collide in the way that, like the computation that Avi showed. And if we really understood how all of this stuff worked properly, we could compare that to what we actually see at different ages, because we can look with our telescopes back to times that were quite early.
Could that pry into what dark energy is or how it functions?
Yes, of course. If the dark energy is too big, as Avi was saying, the acceleration would be early and you wouldn't get the galaxies forming in the same way. Now, it turns out that the tipping point between dark energy kind of being the most important thing and dark matter, or the gravitation being the most important thing, was not that long ago, only about 5 billion years ago. So we see back to times like that. If you go farther back, it's pretty clear that the dark matter, the gravitating stuff, would have been in charge. And so it doesn't matter too much how much dark energy you have when the dark matter or the gravitating stuff is completely in charge. But it's only in the recent time where that has happened, and it probably has a lot to do with cutting off the formation of galaxy clusters, for example, because the expansion is too vigorous in a way, and the galaxies don't fall into the clusters. So you're exactly right. There ought to be a signature of the underlying properties of the expansion written into how galaxies cluster and the evolution of galaxies. We've just done something much simpler, which is to look at these distances. But all that other stuff also ought to fit into that same picture.
Last question.
You are all amazing examples of scientists and folks that have really expanded the knowledge that we have about the universe.
He's setting us up.
And we've had amazing discoveries. We're celebrating a discovery from 50 years ago. More recently, we've seen things like proof of extrasolar planets and that sort of thing. What can we do to encourage our young to go into science now and continue with these amazing discoveries that we've got? We're in a golden age of astronomy right now. What can we do to encourage that to continue?
Well, if you just look at the presentations that were made, most of the stuff we talked about is not really known. We don't know what made inflation, really. What's the field that was driving inflation? We don't know what the dark matter is made of. We don't know what is accelerating the universe. What's the dark energy that is doing this? So basically, we're at a very primitive age right now. We are just starting to get a sense of what's going on, but we don't really know why it is going on. And that's a perfect ground for further innovation, further discoveries. And the people who would make these discoveries are very young right now. And so we should encourage them to get into that game, because we know much less about what we find in the universe than we pretend we know.
Well, so the short answer might be we should have things like public nights at the observatory.
I would like to thank our four guests tonight. Bob Wilson,